Hello friend, welcome to the abstract algebra class. It is class 72. In this class we will explain some important properties of even and odd permutation. Number one, every transposition is an odd permutation. If f is equal to 1, 2, it is a transposition. So it is odd permutation. Number two, identity permutation. I is always even integer, even permutation. I is equal to 1, 2, 3, 1, 2, 3. It is an identity permutation, so it is an even permutation. A cycle of length n can be written as product of n minus 1 transposition. Here we have f is equal to 2, 4, 6. It is equal to 2, 4, 2, 6. Here it is an we have three elements, so we can written as the product of two transposition. 1, 2. N is equal to 3, then n minus 1 way we can write the product of transposition, so it is equal to 3 minus 1 is equal to 2. Then we get 2 transposition, which number 4, the product of two odd permutation is an even permutation. Odd permutation into odd permutation is equal to even permutation. The product of two even permutation is an even permutation. Even permutation into even permutation is equal to even permutation. The product of an odd permutation and an even permutation is an even permutation. An odd permutation and even permutation, it is odd permutation. Even permutation into odd permutation, it is equal to odd permutation. 7, the inverse of an odd permutation is an odd permutation. Number 8, the inverse of an even permutation is even permutation. Here is some example. We want to verify that they are even or odd permutation. Number 1, I'm giving that f is equal to 1, 2, 3, 4, 5, 6, 7. 3, 1, 4, 7, 6, 2, 5. It is equal to 1. Image of 1 is 3. Image of 3 is 4. Image of 4 is 7. Image of 7 is 5. Image of 5 is 6. Image of 6 is 2. Image of 2 is 1. 1 is here. Okay. Now it is equal to 1, 3. We write as multiplication of we want to write as product of transposition. 1, 3, 1, 4, 1, 7, 1, 5, 1, 6, 1, 2. Here is how many transposition we have? 1, 2, 3, 4, 5, 6. Therefore, it is equal to 6 transpositions. Therefore, f is an even permutation. Second one, number 2, f is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Image of 1 is 2, image of 2 is 5, image of 5 is 6, image of 6 is 1. Into 3, 4, 4, 3. Into 8, 9. It is equal to 1, 2, 1, 5, 1, 6. 3, 4, 8, 9. We have 1, 2, 3, 4, 5 transposition. It is equal to product of product of 5 transposition. Therefore, F is an odd permutation. Here we have F is equal to 1 5 2 8 3 2 4 1 5 9 6 6 7 3 8 7 9 4. Then we as example 2 we solve 1 5 9 4 1 5 5 1 9 9 4 2 8 8 8 7 7 7 3 and that is it. It is equal to 1 5 1 9 1 4 2 8 2 7 2 3. If we count 1 2 3 4 5 6, the product of 6 transposition. Therefore, F is an even permutation. Do other example by yourself. We solve number 3, number 4, number 5 as homework. You have to do by yourself. Here is a theorem. We want to prove this theorem. Let Sn be the permutations group on n samples. Then of the n factorial permutations, there are exactly n by 2 or even permutation, and n by 2 or odd permutation. Half is of the permutation is even, and another half the permutation is even. Proof. Let Sn be the permutation group on n samples, then order of Sn is equal to n factorial. We have to prove that among these n factorial permutation, 1 by 2 n factorial or even, and 1 by 2 into n factorial or odd permutation. We now take S equal to E1, E2, E and so on, EP, theta 1, theta 2 and so on, theta Q, where E1, E2 are even permutation. They are even permutation. Theta 1, theta 2 and so on, theta Q are odd permutation. We suppose that this is this whole. Since order of Sn is equal to n factorial, this implies P plus Q is equal to n factorial. Some half of them are even and another of them is odd permutation. So if we take the sum of these two permutation, we will get n factorial. Let t belongs to Sn and t is a transposition odd permutation. Consider the following product: theta E1, theta E2 and so on, theta EP, theta E1, T E2 and so on, T EP, comma T E theta 1, comma T theta 2 and so on, T theta Q. Since Sn is a group here, Sn be the permutation group, so Sn is a group closure axiom hold. It means the product of all these elements are even or belongs to Sn. Since all EIs here are even permutation and T is odd permutation, this implies the product of even and odd permutation, it will be odd permutation. So the number of odd permutation in Sn is Q. Suppose theta EI is equal to theta EJ for some I comma j. This implies EI is equal to EJ by cancellation law for IAJ, which is a contradiction because they are disjoint. So TEI is not equal to TEJ for some I is not equal to J. Therefore, TE1, TE2 and so on, TE are disjoint odd permutation. Hence, from here we got P is an odd permutation. So Q is odd permutation. Obviously, Q is the general odd permutation. It contains all odd permutation. So P is less than Q. It is relation 1. Since T is odd and theta 1, theta 2 and so on, theta Q are odd, this implies odd permutation into odd permutation, it will be A1 permutation or A1 permutation. Then the number of A1 permutation in Sn is equal to P. We know that here the number of, hence Q less than or equal to P. P is the general A1 permutation which contains all A1 permutation. Here these all are A1 permutation. So Q is less than or equal to P. It is relation 1, 2. From relation 1 and 2, P less than or equal to Q, Q less than or equal to P. We get P is equal to Q. Now, since P plus Q is equal to n factorial, this implies P plus, instead of Q, we can write P is equal to n factorial. This implies P plus P, 2P is equal to n factorial. This implies P is equal to n factorial. Therefore, Q also is equal to n factorial by 2. Q also n factorial by 2. P and Q are equal. Therefore, the number of A1 permutation on Sn is P equal to n factorial by 2. The number of odd permutations on Sn is Q equal to n factorial by 2. Hence proof of the theorem. Hence proved. Thank you.